Alright guys, welcome back to the physics of Batman under the Red Hood. This is going to be part 2. Today we're going to talk a little bit about waves, we're going to talk about kinematics, we're also going to talk a little bit about electricity. If you haven't seen part 1, make sure to do that. Also, if you haven't seen this movie, you have to watch this movie. It's one of the best cartoon Batman movies of all time. I might spoil a couple things in the future. I'll be doing part 3 and part 4 very shortly. Besides that, I realize some of you guys might not know what formulas I'm talking about, so I'm going to post a link to the AP Physics formula chart so you can go ahead and pull that up and work the problems along with me. These problems are intended for people that have already addressed maybe the topics, like kinematics, they've already done it, or electricity, they've already done it, and it's just extra practice problems that I'm working through with you guys. So you can get a little bit of extra practice, and you can also see some practical applications. So, I'm going to go ahead and continue with the physics of Batman under the Red Hood. Today we're starting with electricity.
And I almost thought he wouldn't show.
You know what I missed most about running with you? The toys.
Stay sharp. We're not done. You want to dance? Let's dance.
Is that gonna hold?
No.
So you want me to... should I? Okay, I'll just take care of this.
Alright, so in this clip we have Nightwing shooting a cannon at this helicopter, which ultimately takes down the helicopter. Alright, so basically I want to make this problem doable for high school students, so I made sure to draw up a simplified electrical circuit of this helicopter. The actual circuitry inside a helicopter is much more complicated, I'm sure you guys know. I'm going to go ahead and make up some resistance and ultimately the voltage delivered by this electrical cannon. Now in the video clip it's most like an EMP cannon, but that's more magnetism, so we're going to talk specifically about electricity. So here's my problem. If Nightwing's electric cannon creates a voltage of 36,000 volts on the helicopter, which contains the circuit with 4 equal resistors of 400 ohms, as shown to the side, what is the total power supplied to the helicopter that ultimately overloads the helicopter and brings it down? Alright, so today what I want to do is I want to give you guys some actual time. Go ahead and pause the video if you want to work the problem out yourself, and then I'm going to work it out shortly. But this is the time you should pause it, try to work it out yourself, otherwise I am going to continue. Alright, so the first thing we got to do is identify all of our givens, just like last time. We used the guess method. Identify all of our givens, choose our unknown, then pick our equation, substitute everything, and solve. So my first given is obviously 36,000 volts. So that is my total voltage supplied to this electrical circuit. My next given is the fact that each resistor is 400 ohms. That means each one of these resistors has a resistance of 400 ohms. And then last but not least, I want to know my total power. But before I can find my total power, I need to find a couple of other things. First, I need to find out what is my actual total resistance. Not just my resistance of one resistor, but my total resistance of the system. Once I know my total resistance of the system, I can also calculate my total current. And if I want to be able to do that, then I can finally get to power. So by using V equals IR, I can find out all that stuff, and then eventually we'll get to power. First, I want to find out what is my total resistance. Now, in order to find total resistance, we got to simplify this circuit. We've got something called a complex circuit. If you look here, it starts off as a single branch. So we've got this kind of in series with the battery, but then all of a sudden you've got this split right here. Whenever there's a split and there's 2 different branches, that's called a parallel branch. So we got this split up in here, and then it comes back together, and then it continues in series back to the battery. So we got to simplify this part right here to make it in series with everything. Once it's in series with everything, then it's very easy to calculate. But first we got to find out what is the resistance of this little parallel branch. In order to calculate total resistance of a parallel, we do 1 over the resistance of the total parallel circuit equals 1 over R1 plus 1 over R2 plus 1 over R3. However many resistors are in parallel branches. So far we've got 2 resistors in parallel branches. We've got this 400 and this 400. So what we're going to do is we're going to do 1 over R total equals 1 over 400 plus 1 over 400. Now remember, once you do 1 over 400 plus 1 over 400, you're going to get, what, 2 over 400, but that's not your final answer because that's 1 over resistance in parallel. So we do 1 over that to get our total resistance in parallel of 200 ohms. So we've simplified this circuit, this little part of the circuit, sorry, this parallel portion of the circuit into a 200 ohm resistor. Now it's all in series. So we got 400, 200, and 400. To get total resistance in series, all we got to do is add it up, and we get a total resistance of 1,000 ohms. Okay, so now we've got our total resistance, we've got our total voltage. Again, we are looking for total current, so we're going to use this equation again, V equals IR. We're just going to plug it in to get total current, and we get a total current of 36 amps. Now we've got total current, and we've got total resistance. We've even got total voltage, but again, we're looking for total power, so we're going to use something called P equals IV, which is power equals current times voltage. We're just going to plug in our values, and we get a total power of 1 million and about 300,000 watts, which is way more power than any helicopter typically needs. 300 horsepower engine on a helicopter usually only needs about 200,000 watts. So this is way more power, which is clear to see that this would definitely take out the helicopter. Now, electricity. Well, electricity is super important. For one, you definitely couldn't be watching this video right now if you didn't have electricity. You wouldn't be able to use your laptop or your phone to watch this video, and you wouldn't be able to use them for anything else either. Understanding how electricity works means you can calculate the current traveling through wires. Current usually leads to how much power is traveling through a wire, and you can save power, you can use it where you need it, you can make sure that it doesn't overload, because, I mean, again, if you get too much current inside any wire, you're going to create a lot of heat, and ultimately, you could accidentally burn your house down. You can calculate the power in flashlights, all sorts of different things. Electricity is one of the most important units in physics, and you should definitely spend time learning it. Next, we're going to talk about waves.
Think we lost him?
Move! You haven't lost your touch!
And there goes the Red Hood, escaping Batman once again. Alright, so we've got the Red Hood. He's going to shout out to Batman, and we're going to pretend that Batman was walking towards him to make this more of a waves problem. Alright, so we got the Red Hood here on his bike. He shouts out to Batman. And then the train comes in. Oh my god, he disappears. Okay, one more time. One more time. I know you guys want to see that. What? He's talking? He's head toward him? And he's gone. Okay, so this problem, how I interpret this problem to make it more about waves is we're going to say if Batman is approaching the Red Hood at a velocity of about 3 meters per second, when the Red Hood yells out to him at a frequency of 165 hertz, he's got this bass voice, you know. What will the perceived frequency Batman will hear? All right, so he's not going to hear the exact same frequency Red Hood actually gives off. This is called the Doppler effect. When you're getting closer to an object that is giving off a sound, you actually get a slightly higher pitch frequency. And when it's heading away, you guys have heard, you know, police cars travel by you. When they're heading towards you, the pitch is a little bit higher. And when they're heading away from you, the pitch drops down. This is called the Doppler effect. We also need to know one other thing, which is the temperature inside the subway is about 32 degrees Celsius. That'll help us calculate something called the speed of sound. Now, I know maybe these equations aren't on the formula chart, so I'm going to go ahead and start you off with the two equations I'm going to use to solve this problem. At this point, if you'd like to solve it yourself, go ahead and pause the video. I'm going to read out the formulas, though. This is the speed of sound. The velocity of sound equals 331.4 plus or minus 0.6 times the temperature in Celsius. Because it's a hot day, it's going to speed up sound. Then we've got the perceived frequencies. So what you would hear equals the original frequency, all right, times the speed of sound plus the speed of the observer, as long as the observer is heading towards the object. If it's heading away, it would be a negative velocity, divided by the speed of sound plus the source, the velocity of the source. So if the velocity of the source is getting closer or further away. If it's further away, it's a negative again. All right, so go ahead and solve it yourself if you'd like. Otherwise, I am going to go ahead and continue. So the first thing we need to find out is what is the speed of sound. So I'm going to identify all of my givens. Well, the main given is 32 degrees Celsius. Once I plug that value into my speed of sound equation, I get a total speed of sound inside this subway at 350.6 meters per second. Okay? So the next thing I'm going to do is identify my other given, because I'm trying to calculate perceived frequency. I've got 3 meters per second. Now you have to know whether that's the observer or the source. And in this problem it says if Batman is approaching, what does Batman hear? All right, so this is the observer. Batman is the observer, and he's also moving. So I'm going to make sure I plug that value into the observer value. Red Hood, however, is standing still. So what value should I plug in here? Hopefully you guys guessed it, 0. Once I plug in all of my values, oh, again, this is my initial frequency, so I got to make sure I plug that in. Once I plug in all of my values, I get the perceived frequency Batman hears is 166.41 hertz, which is just slightly higher than the original frequency of Red Hood. This might not seem like a lot. I mean, honestly, when it comes to humans walking forward and backwards, you're not going to really notice the difference, but there's a lot of cool things that you can do with the Doppler effect. All right? Not just the Doppler effect, waves are also super important because they're one way you can transfer energy without actually slamming into another particle. Most of the things you learn in physics have to do with the fact that I have to touch an object. In fact, waves, we use waves to transfer energy from the sun all the way to the earth because there's no particles inside that vacuum of space, so I can't get that energy to the earth if it weren't for the fact that we have waves. Doppler effect is pretty interesting. I'm sure you guys have heard of the Doppler radars, which are, in sometimes weather systems. Basically what they do is they bounce off waves against clouds. If the wavelengths or the frequencies are getting shorter, they know the clouds are heading towards them at whatever speed. If they're getting longer, then they can tell that they're heading away at whatever speed. All right, so that's waves. Last but not least, let's talk kinematics.
Got lost.
It's over, Riddler.
Riddle me this. What's green and purple, but covered in red and yellow? You! When I land on your sorry butt.
Oh man, you got the Boy Wonder. So the Riddler's up at the top of the staircase, Boy Wonder comes in, kicks him, and then he falls down the stairs, and then, no, it's not over. He's gonna jump right on him. The problem says, if Robin launches off the steps with a velocity of 18 meters per second at an angle of 30 degrees from a height of 3 meters, how far will Robin actually travel before landing ultimately on the Riddler? All right? So go ahead and pause the video if you need to solve the problem yourself. Other than that, I'm going to go ahead and work through it with you guys. I'm going to again set up everything. So I've got Robin right here. He's going to launch off these stairs with a velocity of 18 meters per second at an angle of 30 degrees from a height of 3 meters. So those are all of my givens, okay? But in order to solve any kind of two-dimensional problem, you need to fully understand that vertical has nothing to do with horizontal. So I've got to separate my vertical and horizontal values. These are all the different things we could possibly solve for in this problem. Okay? So even though it's 18 meters per second as my initial velocity, that's my total velocity going both up and to the right. I want to figure out specifically how much up and how much to the right. In order to do that, we've got this hypotenuse here, and we've got an angle. What if I want to find my adjacent, or my horizontal value, and my opposite on my vertical value? Well, then we're going to have to use something called SOHCAHTOA. Your favorite, I know. All right, so we're going to break up the sine and cosine portion of this 18 meters per second. So if I use cosine, that'll give me my adjacent value, and I'll get a horizontal velocity of 15.59 meters per second. And if I use my sine value, I'm going to get my vertical portion, and I'm going to get 9 meters per second. So we ultimately know that our initial velocity horizontally is about 16 meters per second, and our vertical is about 9 meters per second. What about our final velocity? Well, we don't know the vertical final velocity because it's affected by acceleration. There's something constantly pulling on Robin in up or down direction. Hopefully you guys already identified that's gravity. Is anything pulling Robin to the right or the left? Hopefully you understand once he's in the air, there is nothing pulling him to the right or the left, so there's zero acceleration. If there's zero acceleration, that means that there can be no change in velocity, which means his horizontal final velocity is going to be the exact same as his initial velocity. But again, vertical, I don't know because there is an acceleration vertically. Horizontally, we just said there is no acceleration. Vertically, we said there was an acceleration. There's this force pulling down on him called gravity. Hopefully you identified that that would give you negative 9.8 meters per second. Okay, so horizontal initial value, well, we're talking about how far he is to the left or the right. Because we're ultimately looking for how far he travels, I don't really care about his initial position, so I'm just going to go ahead and put 0 because it doesn't matter. Vertical, however, does. He starts 3 meters above the ground, and ultimately he's going to land on the ground. So we don't know our final horizontal position, but we do know our final vertical is 0. And we don't know time, but time is the only thing that crosses over in these two values, because when you stop moving horizontally, you also stop moving vertically and vice versa. All right, so these are all of our givens. These are all of our givens. Now we need to start solving for what we can actually solve for. Look at your formula chart. You'll notice that for our horizontal values, you can't find x final and time by themselves. There's always something messing up there. There might be a squared or something value that you can't actually solve for either of those. So we're going to look at our vertical values. We've got plenty of information. All right, hopefully you guys identified that the equation you're going to be using is x final equals x initial plus v naught t plus 1/2 at squared. If I plug those values in, I will get 0 equals 3 plus 9t plus negative 4.9 t squared. This is not what you're used to seeing. You're used to seeing one value for x initial or v initial, but ultimately what you've got is you got something that looks like the quadratic equation. So if you use your good old quadratic formula that x equals negative b plus or minus the square root, hopefully you find out that the ultimate time is 2.12 seconds. So I'm going to put that into my vertical side, but what's nice is because when I stop moving vertically, I also stop moving horizontal. I can put that exact same time in my horizontal side. Now I've got plenty of values on my horizontal. So if I really want to find x final, now that I've got time, I can. I'm going to use the exact same equation, except this time I'm only going to use my horizontal side, because again, horizontal has nothing to do with vertical. I'm going to plug all my values in, and I get a total distance of 33 meters, which again is totally ridiculous because there's no way he could launch off at 18 meters per second, although he is, you know, the boy wonder. So kinematics, of course, is seen everywhere. It's basically a lot of physics, like what you mostly focus on when you're learning physics. It lets you predict where any object will land. It lets you predict how long it'll take any object to get there. All right? Basically, once you know acceleration and initial velocity in any kind of position, you can predict exactly where it will be at any given time. This is used in the real world when playing any type of sport that requires you to throw an object, such as football or basketball. You can analyze how fast you need to throw the ball to get it to where you want it to go and at what angle to get the maximum distance, stuff like that. Well, again, I hope you guys enjoyed this video. I will be making more. Don't forget to like and subscribe and let me know what you'd like to see, what I could improve on, because of course I want to make these better for you guys. I hope you enjoyed. Thanks. Bye.